Okay, so welcome, and let me introduce myself. I already know, I think, all of you. Your face is new. My office is just across the corridor. I don't have office hours. When I put office hours, then there's the last minute meetings and I just cannot respect the hours. So instead of office hours, you can just come and ask your questions anytime you can find me. Don't worry if I'm busy or not. I mean, quite often the students don't want to come to my office thinking that I'm very busy. But if I am very busy, I will just tell you so and we can arrange a meeting time. But whenever you have questions, you can just write me an email. If not, you can come to my office. I have tried to start the syllabus of this course on Not the Class. Okay, just some general information. What about the hours, by the way? I mean, I added these 2 hours on Monday. I looked at your schedules, at least as of last week, and these two additional hours seem to be suitable for almost everyone, at least. That is, I didn't see any courses overlapping with these 2 hours on Monday. Now, I intend to do 4 hours a week, mainly because it might happen that I need to go somewhere. So this additional 1 hour a week, we will be using it to make up for the missed hours. And we can, if you have questions, if you want recitation or some discussion hours, additional hours, we can also use that additional hour for that. I will just remove the 3rd hour on Wednesday. Now, any problem with the hours? Ideally, I will be doing 2 midterms, 1 final. We will talk about what the pre-reports are. I intend to give you assignments. Hopefully, at least 10 assignments. It will be from the book, most of them. And the dates, well, we need to determine the dates. Probably we will discuss it on Wednesday. When should we have typically 4 weeks from now, we will have the first midterm. Again, another 4 weeks, we will have the second midterm, and final is determined by the department anyway. I, in general, have 1 makeup exam at the end of the semester. And this makeup exam, if you have a medical report, okay, just come to the makeup. If you don't have a medical report, but you have some other issue, and you just let me know in time, you don't feel like taking the exam, okay, I will let you take the makeup, but just let me know before the exam. Or there are 3 exams, and it happens that one of them is very low, it was not your day, so you get, I don't know, 70, 80 from the other 2, but just 20 from the 3rd one. Okay, it just shows that day there was something, you didn't show your performance, come to the makeup exam. We can talk about it at the end. And just one warning. Okay, the warning will come how we will be doing this course. I don't intend to do you come, sit in the chairs, I lecture type of class. The problem is you don't really learn that way. I advise you to watch this video. I will put the link also in the class. Eric Mazur is a professor in physics, a condensed matter physicist, who is also interested in physics education. He's in Harvard, and at least in this video what he tells is this classical type of lecture just doesn't work. I mean, you don't learn, you learn very few things, and the things you learn, you just forget at the end of the semester. If you want to laugh, there is also another video, 5-minute university. quite often 1 month after the end of the semester, what you remember just fits in that 5 minutes. So, and that is basically a waste of time. I mean, we will be spending something like for 14 weeks on the average 3 hours, that is 42 hours here, plus the time you will be spending out of the class on this material. I mean, what you remember should be more than this, that can be fitted in 5 minutes. Well, to improve that, what Eric Mazur suggests is that you have to actively participate in the lecture. Okay, so in all my lectures I say that you have to participate, ask questions, participate, and it never works. So the way I found out of this is that I don't lecture. So what we will do is I will give you reading assignments, mainly from the book. You will be reading them, trying to understand them. You don't have to understand all of it. But I will ask you to write a pre-report on the weekend before the week starts, where I want you to summarize what you understood and what didn't you understand. And in the class, you will ask questions, and hopefully some other classmate will answer, or we will discuss over your questions. But to be able, for that system to be able to work, you have to come prepared. So that is why I enforce you to give the pre-reports. Now, when I'm lecturing to first-year students, I tell them that if they don't do the pre-reports, I will not let them to take the final exam. They will get an NA. But I just find it stupid to do such a thing for PhD students. I will not force you in such a way. But if you don't do the pre-reports, you will basically don't understand anything about this course, and you will be wasting your 42 hours in semester. I mean, if you don't intend to do the pre-reports, if you don't want to participate in the lectures, I'm sure you can find some more fruitful, more useful thing to do in these 42 hours. Now, one issue with this kind of lecturing is that at the end of the day, you will remember more from this course than you remember from the other style, but it takes a lot of time. You have to spend lots of time. And most of the time, the students complain that it takes too much time because you have to do lots of work on your own. But then when I was looking at your schedules, I saw that some of you are taking something like 4 or 5 courses. I strongly advise against it because that means, I mean, especially if you are doing graduate study, most of the courses will demand your time. And this one in particular will demand even more time. So if you are taking, let's say, 4 or 5 courses, I strongly suggest you either to drop other courses or to drop this one. It won't be useful to you. Now, the first few weeks I will be lecturing still, because we will be using the book by Patria. Okay, so the book is, this one mainly. In Week2 you can download the ebook also, but the Patria doesn't discuss thermodynamics, it just starts from statistical mechanics. But I think it would be, what we will do in statistical mechanics will be eventually connected to thermodynamics. So the first 2 weeks I will be discussing thermodynamics, or mainly reviewing, it will be a fast review of the laws of thermodynamics and how we will use it. And after that, when we start statistical mechanics, I will be assigning you reading material from the book. As I said, I am not expecting you to understand everything in the book. In that case, you don't need to attend the lecture anyway, but try to do your best. What you cannot understand, we will be discussing over here. Any questions? Okay, so let's start with why do we do statistical physics? Well, in fact, if you consider the applications of statistical physics, unless you are doing particle physics, you are always using statistical physics. Even in particle physics, you are, if you are not doing theoretical particle physics, you are still using statistical physics. The basic idea is this one. Have you seen the solution of the three-body problem in mechanics? You have probably seen the solution of two bodies. If there are two objects interacting with a force that depends only on their separation, you can basically solve it. But have you seen the three-body problem? The solution of the three-body? It doesn't exist. No, it doesn't exist. There is no such solution. Even for three objects, three masses, we don't have a solution. Four objects, hopeless. But the nice thing is, as the number of objects increases, the system becomes, the overall behavior becomes much simpler. Now, let's see, okay, how many atoms do you think are there in this pencil, in this pen, stylus? Billions? No, that's a very small number. Anybody remember? At that order of magnitude. Yeah, we have an Avogadro's number, which is something like 10 to the power 23. We have this much atoms here. Now, three-body problem, we cannot solve it numerically, analytically, or four-body or five-body, except in certain special cases, but we can still solve them numerically. We know the solution of the three-body problem, four-body problem, at least for a short amount of time. If they show chaotic behavior, we cannot make predictions for a very long time, but for a short amount of time, we can still do some decent work. Well, let's see. We have this much particles. If we want to solve this numerically, of course, just forget about quantum mechanics for the time being. How much memory do we need to store the initial values? You see, the initial values, if we treat this problem classically using Newtonian dynamics, we need 3 momenta and 3 coordinates for each particle. So we will need typically 10 to the power 23 initial values. Well, depending on how precise you want these initial values, you might use 1 byte or more bytes. Let's say that you use 1 byte for each initial value. So how many bytes does this make? What is 1 megabyte? Well, that is what I find easy. This is 10 to the power 6 bytes. 1 gigabyte. This is 10 to the power 9 bytes. 1 terabyte. 10 to the power 12 bytes. How much do we need? We need around 10 to the power 11 terabytes of storage just to store the initial values. I think the largest hard disk now, they are talking about 100 terabytes, but still that means we need 10 to the power 9 of them. That's a huge number. But huge numbers also have one simplifications. Let's say you are trying to calculate some quantity. Let's make you make some error in calculating that quantity. How much error do you think is acceptable to calculate any quantity? 10%? Is it acceptable? 1% is acceptable. Let's use something large. Let's assume that we calculate something. Yeah. Okay. How much is acceptable?
I don't know the exact formula, for example.
Forget about the formula. I mean, let's say that I give you some information. Let's say, for example, if I give you this one, and I tell you that this is like 20 degrees, okay, you will grab it. But if my error bar is something like 100 degrees, that's not acceptable for you. So it might burn your hand or freeze your hand. Now, typically in statistical physics, we will be calculating certain quantities. Let's say we make an error of the order of, by a factor of, I don't know, 10 to the power 6. We miscalculated by 10 to the power 6. That's huge, right? But you see, we will see that most of the time, the quantities we will calculate will go like 10 to the power n being the number of particles. But then this means this is approximately 10 to the power n plus 6, which is approximately 10 to the power n. Negligible. So that is also something we need to keep in mind. We don't need to calculate everything precisely. We can make huge errors. You see, an error of a factor of 10 to the power 6 is negligible. Even if you would say, I don't know, 10 to the power 1 million, that would be a negligible error when we are talking about thermodynamics, or huge numbers. So what do we do? Okay, so we said that, okay, on one hand, studying such systems with 10 to the power 23 degrees of freedom, even numerically, forget about it. Maybe, I don't know, in 20 years, I mean, even if you go with the Moore's law in the storage, probably it will take a very long time to reach a state where we can easily store this much information, let alone manipulate that information. So what we do, we change our questions. That's the first thing we do. So what would you like to know? Let's talk about this eraser. What would you like to know about this thing? Okay, we had already discussed, you would like to know its temperature. So you have to determine whether it will burn your hand or freeze your hand, or you can comfortably hold it. We would like to know its temperature. I don't care about what each one of the atoms in this eraser does at a given moment. That's just, for me, so what? I don't care about it. So what else would you like to know about this? Okay, I know it's not such an exciting object. So what else would you like to know?
Some phase information like boiling temperature, freezing temperature.
Temperature and boiling temperature. Okay, that's nice.
Some
Phase transitions. For example, in this example, I wouldn't like to touch it if it isn't melting. What else? Composition. Density. I don't know, for example, if this has the density of a neutron star, I wouldn't like to try to lift it. That would be tons. Of course, that also, to calculate its mass, I would need to know its volume. You might need to want to know the pressure. You might want to know its velocity, center of mass velocity, energy. Anything else? Conductance, if you want to use it in a circuit. Already you are having a hard time to come up with something else. So you see, on one hand, if we want to describe this exactly, we need to determine of the order of 10 to the power 23 degrees of freedom. On the other hand, what we really care about is just, let's say, 10 or 20 properties of the system, not 10 to the power 23 properties of the system. So statistical physics or thermodynamics, what it tries to do is tries to describe a system in terms of only these properties, these so-called macroscopic properties of the system. That will be our aim. Well, there are basically two approaches. Thermodynamics. Well, this is basically, this evolved from the need to understand heat engines in the industry during the time of the Industrial Revolution. So we want to build more efficient heat engines. So that's why it is thermodynamics. But what thermodynamics essentially does is, well, we have all these macroscopic properties. So it relates the macro world to the macro world. This is what thermodynamics does. It expresses one thermodynamic property in terms of the other ones. A well-known example, the ideal gas law, PV is equal to NKT. So temperature is a macroscopic property, pressure is a macroscopic property, volume is a macroscopic property, the total material, you can put either the total number of atoms, the mole number, or you can convert it even into some expression involving the mass. Basically, this is a relation between the macroscopic properties of the system. And well, there are certain systems which respect this relationship, certain other systems which do not. But even in systems which respect these, we don't know, thermodynamics doesn't tell us why there is such a relationship. Because it doesn't relate this relation to the microscopic properties of the system. And that is where the statistical physics comes into the game. So if you have a microscopic description of your system, for example, we will see that if you have a non-interacting collection of particles, we know their interactions, they don't interact, we know their microscopic description. And starting from that microscopic description, we can obtain the proper relations between its macroscopic properties. We will be deriving PV is equal to NKT for this simple system. Each one has its advantages or disadvantages. For example, thermodynamics, we could develop thermodynamics without even understanding the atom itself, basically because to use thermodynamics, you don't need to know the microscopic description. But at the same time, it is limited. For example, thermodynamics tells us that PV is equal to NKT for certain systems. We can experimentally determine which systems satisfy PV is equal to NKT, but we cannot have a deeper understanding. But statistical physics tells us under which conditions PV is equal to NKT is valid. But the problem with statistical physics is that you first have to have a microscope. You have to have an understanding of the microscopic properties of the system first, and from the microscopic properties you obtain the macroscopic properties of the system. Both have its advantages and disadvantages. And as I said, what we do in statistical physics is we'll be eventually trying to calculate some thermodynamic properties using this microscopic description. And since thermodynamics allows us to relate various thermodynamic properties among each other, then we will be using thermodynamics to obtain the other properties. So that will be kind of the purpose of all this course. How, at least in simple systems, how we can start from the microscopic description, how we start from the Hamiltonian of the system, whether you do classical physics or quantum statistical physics, with how to start from the Hamiltonian, obtain the thermodynamic properties. Any questions? Okay, so let's start with the first law, the zeroth law. Have you heard of the zeroth law of thermodynamics? Anybody who knows the zeroth law is? Well, basically this was discovered after the third law, so but it's more fundamental than the three laws. So that's why people just called it the zeroth law. And basically, if A and B are in, A and C are in thermodynamic equilibrium, and B and C are in thermodynamic equilibrium, then A and B are also in thermodynamic equilibrium. Well, first of all, what is thermodynamic equilibrium? It is basically a state of the system in which no energy, matter flows within the system. For example, our running water is not in thermodynamic equilibrium. There is a flow of water. If the water is running such that all its parts are moving at the same velocity, when you go to the center of mass, you can say that it's still in thermodynamic equilibrium. If you have two objects at two different temperatures, if you bring them in contact, there will be a flow of energy. It's not in thermodynamic equilibrium. Eventually, all the systems, if you wait long enough, they will reach thermodynamic equilibrium. Now we will be discussing this what we actually mean by equilibrium in more detail, because basically equilibrium also means that it depends on the relevant time scales. For example, we know that the universe is expanding. So nothing is in thermodynamic equilibrium if you consider time scales of the order of the age of the universe. Everything will change. But let's say during this classroom, during this hour, this sponge will still be in thermodynamic equilibrium, because in that time scale it does not change. Now, in this course we will not be studying systems that are out of equilibrium, but for example, if you have two objects at different temperatures, you put another bridge, let's say, in between them. The system is not in thermodynamic equilibrium, but if you divide it into very small parts, each small parts momentarily can be treated as in thermodynamic equilibrium. Or if you have a piston, if you are moving the piston, in that case, if you are moving it slowly enough, then at each instant you can still approximate your system as if it's in thermodynamic equilibrium. But then, of course, what do you mean by slow enough? Well, for a gas, the scale of speed is determined by the speed of sound. Well, speed of sound is quite fast compared to many cars, so the piston can still be moving very fast compared to, the speed of the car, but it can be considered as slow compared to the speed of sound in that medium. Anyway, we will be discussing it later on. Let's come back to this zero flow. So can anybody make any sense of it? Except as saying that, well, isn't it obvious? So what does this really mean? Because that's probably why people discovered it the last, because it was kind of something obvious. So people just took it for granted. But you see, what this means is, basically, there exists a quantity which we can use to determine, to classify systems in equilibrium. Well, let's say what does it mean, how we can use it. Let's say we take many different systems. They are not in equilibrium with each other. Let's call them, this is A1, A2, just give them some names. And then if you just give me an object which is in thermodynamic equilibrium, I can just look at all these ones and determine with which one it is in thermodynamic equilibrium. Then I can group all such systems in thermodynamic equilibrium together. They will just form a group. In the physical sense, I'm just classifying it. So I take this one. If this is in thermodynamic equilibrium with A2, then I put it in the group of A2. I take something else, If this is in thermodynamic equilibrium in A3, then I group it in A3, etc. But that also means that without referring to this one, I can call this as 2 because it's in equilibrium with A2. Why did I choose such weird names? I could have, instead of choosing A1, A2, I can just call them 1, 2, 3. So then this will be 2. But I can also give it some other name. I can say that number to be its temperature. So that is the quantity which classifies systems in equilibrium. If I have a system in equilibrium, I can just choose as many such scales as I want. It will be in equilibrium with one of them, and I can just assign some number to it, and that number I can call the temperature. So zeroth law basically states that there is a quantity called temperature. Now we will be more precise in defining the temperature. But for the time being, the zeroth law only tells us that it is possible to define a quantity which determines whether two objects are in equilibrium or not. If the two objects have the same quantity, then we will know that they are in equilibrium. And this quantity we will eventually call, that is one of these quantities, let's say, we will call the temperature. This is the zeroth law. Now let's come to the first law. Do you remember the first law? You can call it the conservation of energy. It says that delta U is equal to delta W, delta Q minus delta W. Now let's see what each of these quantities are. U is the internal energy. Q is the heat given to the system. If heat is taken away from the system, it just means that, delta Q is less than 0. So delta Q is always the heat given to the system. And then delta W is the work done by the system. So if work is done on the system, in that case delta W is less than 0. Okay, so let's start with work. We talk about work, but what is work? And then we will talk about heat. What is heat? Well, in fact, let's start with the heat. Well, the heat is this is the definition of heat. Anything that causes the change in the internal energy of the system, that is not the work. That is the definition. Now, later on, we will also discuss systems in, let's say, electromagnetic field. If the system has a magnetization, if you put it in a magnetic field, it will also contribute to the delta U. We will separate that one also, but everything else is, we call heat. So,
what's the difference between internal energy and total energy?
well, let's see. Can you estimate your total energy now? just make up some number. 10 to power 20 joules. Okay, 10 to power. I can say that, well, no, it's 10 to power 50 joules. Both will be correct. First thing is, regarding which observer are we talking about? Now, yes, internal energy is usually defined as the energy of the system in its rest frame. If you are at rest, there is still some energy. And this energy is due to the kinetic motion of the particles making you, their potential energies. If they are external, their potential energy is due to the other particles in you, plus the potential energy due to the external force, external potentials. But your overall translational energy is not included in this delta U. Let's go to your rest frame. You still have some internal energy. You still have some energy. That's called your internal energy. Now let's look at the work. What is work? This is freshman. Oh no, at least half of you are assistants. You are teaching the labs. What is work? Yes. This is the work. Now, of course, here we won't be dealing with point objects or rigid bodies. You are dealing with a system with arbitrary shape, arbitrary properties, etc. So let's see. Let's assume that we have our system has some kind of a boundary. We are in its rest frame, so we are not considering the work done due to. Well, okay, let me not say it, but. We are not interested in the overall translational motion of the system as a whole, but we are more interested in the changes in its shape. So this is our object. So let's say it changes its shape, and after the change in its shape, it takes such a new shape. It's not really important what the actual shapes are, a very small change in the shape. So what happened was, let's say we have a segment over here. There is a segment over here. Let's call that area of that segment dA. It is displaced by, now it's over here, it's displaced by dL. And is there a force on it? Well, let's assume there is a force acting on it, an internal force. So dW will be F, or let me put it this way, F over dA times dA well, dA is actually an area vector. Do you know the area vectors? Are you familiar with area vectors? So let me just denote the dA vector to be perpendicular to the area, and the magnitude is equal to the size of the area. So this is the work done, dA.dL. But dA.dL is nothing but this volume over here. So dW is F over dA times dV. And F over dA is usually called the pressure. Well, I just skipped some detail that in the definition of the pressure, it has to be the perpendicular area, but in the expression of dW, the force is also the perpendicular force anyway. in the direction of dA. So dW is P times dV. Well, there's one problem over here though. I mean, we define the pressure as the force per area. Now, usually we will be talking about the pressure. When we are talking about the pressure, we talk about the pressure of the system, not pressure at that point. So if you want to talk about the pressure of a system, you have to make sure that the system is in what's called a mechanical equilibrium. The pressure exists only if there exists mechanical equilibrium. Because pressure is basically an average quantity. Now, you can of course say that, I mean, if you have more complicated systems that are not in mechanical equilibrium, you can still talk about, for example, systems in quasi-mechanical equilibrium, meaning that there is not the pressure of the system, but if you look at very small parts of the system, you can see that for that very small parts, you can treat that small part as if it is in equilibrium and define the pressure locally. Or if the system is changing with time, but changing in time sufficiently slowly, then you can say that, okay, you can define the pressure at a given point at a given time. But let me give another example where you cannot really talk about the pressure of the system. Let's say you have some gas. And then you remove the barrier. When you remove the barrier, the gas atoms will be just moving randomly around. If you try to calculate the pressure, measure the force acting on, let's say, in this area, well, in that case, what you will see is, if your measurement equipment is precise enough, until the system reaches mechanical equilibrium, what you will see is no force. Maybe one of those molecules are moving fast toward that area, then you will have a peak in the force, then no force for some other time, then two peaks, and no force. So in that case, it doesn't make sense to talk about the pressure. So force as a function of time will be zero, some force, some more force, and then it will reach some stable value.
But when we change our time scale, we should see something like pressure with a function of time,
Yeah, this is the graph. If you have a precise enough equipment, then you can actually see this thing.
Okay.
But most of the time, we don't have such precise equipment. Okay, now any questions up to here? dW is PdV. Well, let me make it a bit more precise. Remember what is the pressure? Pressure is the pressure of the system. dV is the change in the volume of the system. And then we said that dW, well, let me put this bar there. We will come to that. Why do we put that bar in a moment? We know that this is PdV. But before I ignore the signs, so what should be the sign, positive or negative? Remember how we define the sign of dW. Work done by the system. If the system is doing work, then dW has to be positive. That is, if the system, let's say I have my system, it is at some pressure, it is expanding, pressure is positive, dV is positive. If dV is positive, dW has to be positive. So the signs are fine. Now let's see. Let's calculate some work done. Suppose I have a system. I can talk about, and I'm changing the volume of the system. The pressure of the system is changing. Let's say that initially my system is at this point, at this volume V1, and at a pressure P1. And then after all the changes, the system has a volume V2, and it has a pressure P2. What is the work done? Well, this much information will not be enough to calculate the work done. Now, let me give you some more information. Let's say initially I start from P1, I keep the pressure constant until I reach the volume V2. And then once the system reaches V2, I drop the pressure to P2. Let's say this is state A, this is state B. I have an intermediate state C. So let's calculate the work done as we go from A to C to B. Well, what is the work done as I go from A to C? Well, the work done will always be PdV. From A to B. Yeah, that is from A to C, and then from C to B. Well, the easiest one is to go from C to B. What is dV as I go from C to B? I go from C to B. What is the change in the volume at every step? 0. So dV is 0, so this is 0. And from A to C, the pressure is constant at P1. The total change in volume is V2 minus V1. Okay, this is the work done as I go from A to B, passing through C. Well, let's look at some other alternative. Let's say I start from A, but this time I first drop the pressure of my system, then increase the volume. The work done as I go from A to D, then to B. Well, again, from A to B of PdV, which is from A to D, PdV, plus B to C, PdV. What is from A, no, sorry, this is from A to D, and then from D to B. Well, what is the dV at every step as I go from A to D? 0. This is 0. And the second one, pressure is constant. This is P2 times V2 minus V1. And it is definitely not equal to as I go from A to C to B. Well, you see, the initial state is the same, the final state is the same, but the work done will depend on how I go from an initial state to the final state. So because of that, it doesn't make sense to talk about the differential of W, because the differential of something is the difference as you go from some initial point to a final point. But that difference in the case of work doesn't have any meaning if you don't specify how you go from the initial to the final point. It's not an exact differential. So dW is not the differential or similarly delta W is not the difference of W. Or put it in a different word, W, there doesn't exist a so-called state function, whose difference gives you delta W. Delta W is just not the difference of a function evaluated at two different points, which will be in contrast to, for example, the energy. When I look at him, in principle, if I know again speaking Newtonian, from the Newtonian perspective, if I know the position of his atoms, if I know the speed of his atoms now, I know his energy. And if he comes comes here, starts to jump up and down, his internal energy will increase. At the end of that process, I can still calculate the energy. And the change in the energy, internal energy, will be just the differences of these two energies calculated at two different points in, let's say, the PV diagram. So energy is a state function. I can talk about the energy of the system, but I cannot talk about the work of the system. The work done is, in a sense, essentially a property of the change itself, not of the system only. Any questions? Let's give a 10-minute break, and then we will continue.